Hey there, my name is Erick Trevino, and this is my constant velocity lab. So, to begin, we need to discuss some fundamental physics principles. So, Newton's first law says that an object stays at its current state unless acted upon by external force. So, it stays at rest as long as there's no force, and it stays in motion, which is constant as long as there is no external force. So, in relation to this lab, since the net force is equal to zero under constant velocity, if we look down at the velocity update formula, since the net force is zero, the initial and final velocity throughout this experiment should be the same. And looking back at the position update formula, this means that our position, all we have to do is multiply the velocity times the time and add it to the initial position, which should be zero. And so the purpose of this lab is to record the distance of Marcus motion, the Marcus motion at constant velocity, which is all experimental, which means, in nature it's not perfect. And by doing this, we're comparing this motion to a simulation in a computer, which is more theoretical. And now, one key assertion I need to make is that we're assuming friction is a non factor. Okay, bear with me. So, in terms of free body diagrams, when I initially push the marker, there's initial force, which means the net force isn't zero, but that gives it, it applies to Newton's first law, where since I'm applying a force, it's going to stay into motion. And then eventually, once that force is gone, there's no forces. There's the net force is zero as normal force and gravity cancel out, which means it should theoretically be going under constant velocity, as the system, in this case being the marker, should be constant, whereas the surroundings, shouldn't really affect as much. And the surroundings could include anything such as the ruler, the table, anything like that. And this is a screenshot of my tracker analysis just to demonstrate, what I did. And within that data, I was able to find the velocity by going to the first two lines, the time of 0 seconds and time at 0.033 seconds, with the positions at those times right here. And I used the velocity update formula to do distance over time. I rearranged the variables. And by doing this, I got the velocity final, which should be the velocity throughout, to be negative 0.1159 meters per second. And each frame was taken under every 0.033 seconds per frame. And this is what the conditions will look like in the computer simulation. So I just plugged the initial velocity and the initial position coordinates. And in relation to Newton's second law of the position update formula and velocity update formula, this is what those formulas will look like in the computer. Which, they could be a little messy, but that's why I put the written one above to, I guess you could compare and see where everything goes. And this is the iterations. So, like I said, you knew second law. This is what the computer simulation is gonna run to graph its results. And these are the results. So the lab is in blue, which is what I did, my experimental model, and the red is what the computer did. It's in the simulation. And as you can see, there's some stark differences. Like around zero point 0.3 seconds, it began to differ a little bit, as I mentioned here, which could be due to a variety of reasons, right? So I'm a human, so I have human error when finding the point path on the tracker, which leads to misled data. In addition, I may have just simply rounded wrong, and although I didn't want to mention it, I failed to account for external surrounding factors such as friction, which, have an important role. But initially the velocities are relatively the same, but they do begin to differ eventually. And now one key question is, what if the axes were flipped? Well, in this case, the direction of velocity would just simply change from its negative direction to positive direction, which this only impacts the y direction values as the position changes, but the magnitude stays the same. And what does this mean in terms of net force? In terms of finding how many push pull forces are in this case. So the question is basically asking, am I able to count how many there are? Which it's possible because we know no more force and gravity are at play as they cancel out in the y direction. And friction air resistance are also at play, which I didn't in this play I didn't count for it, but they can be. And beyond that, I don't really know what other additional force could be applied. So, in a sense, you probably could say you could take a good educated guess, but there's no guarantee to know how much forces are given to net zero. But it's possible. But yeah, that is my physics one lab, and I hope you have a great day.